Hello, sir. Come back with the next case. Case one is UPFC with the GA. As you see, we have two cases, GA for optimization and GA plus I-GWO. The first thing is the mini program. The mini program to initialize something. The first thing is to clear and CLC the command window and clear all the workspace variables, and then after that we have some initial parameters like the base MVA, the optimization algorithms, which is the problem object, and the number of variables that we want to optimize, and the lower band and upper band. This is the lower band contained, as you see here, we have two UPFC. Each UPFC have three parameters. The first parameter is the voltage, the voltage that we want to add it, and the second thing is the angle of the UPF, and the third one is the location of UPFC that we want to optimize, and then the same thing for the other UPF, as you see here. The voltage magnitude, the angle, and the location that we want to optimize. And as you see here, we have the lower band for these variables and the upper band. This is the limit of the variable that we want to optimize. And then we also define some number of chromosomes, the cadence solution, and the number of genes variables, and the maximum generation of maximum iteration, and some parameters that we want to use in the GA optimization and visualization, also for the convergence curve. And after that, now we started with the genetic algorithms, and then we get it the best optimization variables value, and we applied on the object functions, and we get it some the results that we printed. After we get it the voltage, as you see here. We get it the voltage at each buses and plot it in the graph, and then we display or printed the result like a voltage of UPF, angle UPFC, and also location of UPFC, and then we also printed the power loss, reactive power loss, total system load, the total transfer capabilities, and the total transfer capability, power ascending and the receiving it, the power flow limits, and the loss of the load. This is after we applied the best values of the variables. So the program now optimized that variable of UPFC, and we get it the values, and this is value applied on the object function to get that result that we printed in the main program. If you go to the optimization algorithms, and now as you see here, we have the output and we have input of the genetic algorithm optimization, and the first thing here, to initialization the population, initialization the variables that we selected randomly. As you see here, initialization program, we get it uniform randomly of the variables. This is number of variables, as you see here. This is number of variables, 40 number of chromosomes. Here we generate 40 population and chromosomes randomly, dependent on the lower and upper band, as you see here. This is randomly, and after we this is population, initial population, it is randomly initialization. We applied on the object function, as you see here. We applied on the object function to get the chromosomes and the fitness of the value, the value that we get it. The fitness, it is the total the fitness, it is the total transfer capability value. When we decrease, this is the values, we that means the best result. And also the gene that we get it. The genes for each populations. We will explain what is the this is output when we explain the object function. And after we initialization this thing, now we sort this chromosome, population chromosomes, dependent on the value of the fitness function. That means ascending. That means the population that has the minimum fitness, we will put it in the first, and the value of the fitness is the largest one is put it in the last values. And after that we put in the convergence curve because we need to plot the convergence curve, how to the optimization function behavior with the iteration. So we put it the convergence curve, the fitness value of the best one population chromosome. And then after that, now after the initialization process, this is the initialization process that we initial, as we mentioned, explained before. We initial the population randomly and apply it on the object function to get the fitness of the population. And then we sort that dependent on the ascending that dependent on from the smallest to the largest one. And after that we started with the main loop now, or the main genetic algorithm loop. As you see here, we started from 2 to the maximum generation, repeated that. This is the process. It started from the main loop is started from 28 to 62 and 63, and repeated this process until to reach the maximum generation that we defined as 100. The first one is to calculate the fitness values, as you see here, for each population. Now we get also this is population. We limited by the lower band and upper band, and then we calculated the fitness value of each population chromosomes. And then, as you see here, we go to the section of the selection process on the genetic algorithms. The section, the selection function, we have the selection, the best population. How to do that? We have we make the scaled fitness for each fitness population, divided with the sum of this is scaled. You mean that we make some normalized of the fitness values, and after we normalized, we sorted that, as you see here. And dependent on the sorted, we get the new chromosomes and the new temp chromosome population, and then we get the temp population fitness, and after that we get also the temp population normalized, as you see here. And after we make some checksum. This checksum, or it is this is the checksum to the temp population chromosome normalized, and after that we calculated the index pattern 1 and index pattern 2 also, and started to the loop. This is loop to calculated the pattern 1 and pattern 2 to make the selection. And this is pattern 1 and pattern 2. It is output of this selection process. And dependent on pattern 1 and pattern 2 also, we go to the crossover of this genetic algorithms. And it is the single 1. As you see here, this is the crossover. To calculate it, child 1 and child 2. Depending on the pattern 1, gene 1, the length, and then we apply the limits, randomly crossover limits. And this is the part 1 and part 2 of the pattern 1 and pattern 2 genes. And then we calculated, depending on part 1 and part 2, child 1. And depending on the part 1 and pattern 1 and pattern 2, we calculate also part 1 and part 2 to calculate the child 2. And this is the single, not double case. And then we, from this child 1 and child 2 genetic algorithms, we go to the, as you see here, after the case. Now, if some random variable, it is less than PC number, the child 1 equal child 1, else the child 1 it is equal to pattern 1, and so on. And after that, we output the child 1 and child 2 to the genetic algorithm. And after we cross over this pattern 1 and pattern 2, we got the mutation. Mutation also depends on the child 1 and child 2, that output of the crossover to calculate the new child 1 and child 2, depending on the PM variable that we initialized, 0.001. And as you see here, where is the mutation? Depending on the child 1 and child 2, and mutation, a PM mutation. If the PM, this is the random one, if the random is less than the PM, the child, we change the child, we not, or reverse the child in genetic. If not, we will stay the same thing. And after we mutation, we get it a new genetic algorithm, new population, chromosomes, and apply the limit of lower and upper band, and the same thing for the new population of the next one. We applied the lower and upper limit, and after that, now we go to the to calculate the fitness of the new populations by applied the object function, and this is the fitness. Go to the elitism. In elitism, it is compare between the new population and the old one to get the best one. The output is the best one. As you see here, we compare between the population, old population, and the new population, and to get the best population dependent on the fitness values, the best new population with the old, compare between them to get the best population from the best one. So not the best then population from the old, the better population from the elite, and then set it in the year population. And this is the year population after God. This is the year population. When we set it in the conversion, it is the year population. Yes. Put it in the conversion, and this is the new. Put it in the original population. And the original place that radius, say the yearly name. And then we finish it back to the different, and they can get this process. But what about synonymism? He summarized that. The first thing to calculate is the thickness value of the population, and then he make for the to select the pattern, the crossover to crossover between his batch 1 and batch 3. to see, make some mutation on the child 1 and child 2, the output of the crossover, and then we generate the new population. This is the new population applied on the object functions, and then we make elitism. This is elitism to compare between the population, the old one, original one, and the new one, and to select the best from two population, the best from the population and the new population, and put it in the original, replace the previous population with the newly made one. And also to print the convergence, to store the fitness, the best one fitness in this loop in the convergent iteration, and display that also the number of iteration and the convergent values in the command window. After we finished from this main loop, now we store in the best chromosome, the best population chromosome gene, and also the best fitness values of this chromosome. This is the chromosome. The population is, as you said before, it is contained for 2 UPFC, the voltage magnitude, and the angles and the location for the UPF1, and the voltage magnitude and the angle and the location of the UPF2. And after that, as you see here, we plotted the convergence factor, how to the convergence curve behave with with the iteration, and then we go back to the main loop, as you see here. And this is the best chromosome we applied on the UPFC cases in the genetic algorithm to print the result and get the result about the power flow, power loss, reactive power loss, UPF location, power demand, power flow in each lines, and all the other results that we explained before. We hope to be clearly about how to optimize the UPFC location, magnitude, voltage magnitude, and angles. Thank you very much for your listening. We will explain the other code in the next videos.